So this is the second half of our OS design pattern discussion, and to me it's the one that's actually really exciting because it's an interesting approach that people came up with a long time ago, but then it didn't really pan out. But then people started getting interested again, and it started showing more promise. So to me, it's really exciting. If I were to build an operating system from scratch, it would probably follow the design patterns that we're going to discuss today. But we'll get into it pretty quickly. These were the... Oh, yes, sir.
Before you start, are you here on Wednesday? Or?
I am not here on Wednesday. In fact, I am not here tomorrow. So do you need something? Or?
I was wondering when do lectures stop?
Lectures stop at the end of today. Yeah, they'll be back in 2 weeks. I'll send emails. I'll send messages so that you remember. Obviously, all the lectures are recorded, so you can watch those. But yeah, I'll miss you all. I mean, I'm really sad I'm not going to get to have office hours because it's always fun to help people with this stuff during office hours. But we do have 2 TAs, highly skilled, qualified people. So there'll be office hours tonight and then tomorrow night and then 2 more sets of office hours on Wednesday night. So you'll have plenty of support. And you can always ask questions on Piazza. I will do my best to answer as quickly as I can. Okay, so these were the design patterns we discussed already. So simple structure, aka not really structured. Layered structure, monolithic, and modular. So these, like modular is kind of what we have today. Especially Linux is a really great example of a modular kernel. And you may be familiar with sort of the back and forth that happened between Linus Torvalds and I think Andy is his first name, Tannenbaum, about modular versus, monolithic versus microkernel architectures. And the big appeal of monolithic is it's fast because everything's inside the kernel you can access. And the downside, fragile, it can explode easily. So. We also talked about separation of policy and mechanism. Remember, this is the thing that is really common in operating system implementation because mechanism is kind of hardware. It almost never changes for a particular platform, but policy can change all the time. You can come up with a lot of ways of improving policies to get better results, and so it's nice to have those 2 things separated from each other in the design. So this is where microkernels come into the picture, and they ask a very important question, which I kind of talked about briefly previously, which is what actually needs to be in the kernel? Remember, the kernel is the part of the OS that runs in kernel mode. What actually needs to be in kernel mode? Does your printer driver need to be in kernel mode? Does your file system need to be in kernel mode? These are the questions that I think are important to ask if you're designing an operating system from scratch. And so basically the only parts of the OS that have to be in kernel mode are things that do kernel mode type things specifically. So I'm changing memory mappings, process address space mappings. I'm manipulating registers because I want to do a context switch. That kind of stuff. Yeah, receiving interrupts is a great example as well. Okay, so the OS structural approach that is really clean and is just sort of like very pure from an abstract and an architectural standpoint is the microkernel architecture, which basically says I want to only have things in the kernel that really need to be in the kernel. And so basically anything else that the operating system provides is a user mode process. That's just the rule. Okay. And so the question is, what should you actually have inside the kernel? Typically, it's narrowed down to basically 3 things. And the rationale for it is provided by this minimality principle. This guy, Jochen Liedtke, has really made giant contributions to microkernels. The problem is that he unfortunately passed away in 2001 car accident. So, it's really sad because sometimes these people are cut off as they're making huge contributions to computer science. But anyway, so he had this principle, which is a concept is tolerated inside the microkernel only if moving it outside the kernel, i.e. permitting competing implementations, would prevent the implementation of the system's required functionality. So if it breaks the OS to move it outside the kernel, then we leave it inside the kernel. Otherwise, we get it out. Okay? That was his idea of how to design these microkernels. So this tends to be the minimal set of functionality. Some way of having schedulable concurrent threads of computation. And you'll notice here we call it a process abstraction. That's because we haven't talked about kernel threads yet. But some means of providing concurrency and context switching. So then we have memory abstraction. Obviously requires interacting with the computer hardware as well. So how do I put that firewall between processes and make sure that they can't actually mess with each other? Also, how do I protect the kernel from user applications? And then the last one, when you have this kind of approach, you need some way for processes to communicate. And so that's where this inter-process communication, aka IPC mechanism, tends to be provided. Okay? So I have to have this so the user mode processes can interact. Okay? These are the things that have to be in the kernel. Okay? And like I say here, it's basically not possible to build a kernel with these things in user space. It just doesn't even make any sense, because how would you even get to that code to invoke those features if those are the features that are necessary to do that kind of invocation? Okay? What you find is that microkernels are tiny. And that's what I think is so cool, because once you learn the basics of how operating systems work, you can build a microkernel operating system, or at least the kernel of it, you can build relatively easily. They tend to be less than 10,000 lines of code. Okay? Anybody who's taken CS122, NanoDB is like 60,000 lines of code. So a microkernel for an OS is way smaller than that. Anybody here familiar with Minix? Heard of Minix? So Minix was Tannenbaum's operating system that was sort of trying to get some kind of traction about when Linux came along. And Minix is used for education. Minix's kernel is about 6,000 lines of code. Okay? So tiny, tiny OS kernels. And when you have fewer lines like that, it's easier to get them correct. And so that's the whole premise here. Everything else is user mode. Now notice even things like device drivers, file systems kind of make sense, but device drivers talk to hardware, so that's kind of an unusual one. Even virtual memory pagers. Okay, so those are the things that figure out what page should be evicted and so forth. So basically, microkernels are really taking this whole approach of separating policy and mechanism as far as it can possibly go. Okay. Let's see. Yeah. Now you'll notice that some of these things do require hardware interaction, and so frequently microkernels also include the ability for drivers to be able to talk to hardware directly, and so those things can be granted access to hardware in some controlled manner. So you can see that maybe you can benefit from using the other protection levels in the hardware to support this kind of thing, so that drivers can have greater access even further than a user application would. Okay. Also, you'll notice process scheduling is an interesting question, because process scheduling is the kind of thing where it makes a lot of sense to have multiple competing implementations. I want to have this kind of scheduler. Maybe I want to have a hard real-time scheduler. I want to have a soft real-time scheduler, things like that. The problem is context switches are not cheap, right? We talk about this some in CS24. We've talked about it a little bit more in this class. Switching to another process, trapping from kernel mode to user mode is not free. And so it kind of seems expensive to have process scheduling live outside the kernel. So this is a great example of where microkernels are a great ideal and they're a great abstraction, but sometimes it's just a bit too costly to go ahead and fully commit to that idea. So process scheduling frequently ends up inside the kernel because it's just cheaper to implement it that way. All right? So that's one of those interesting things. Let's see, text editor, create and save a file. Now this is a really simple sequence of steps, but I want you to think about this from the perspective of a microkernel. You're all getting some experience with that, writing your command shells, how you would do this, from a typical user mode process. I need to create and save a file. Okay, so I open the file and I write data to it using the write call, and then I close it, something like that. So a few system calls, no biggie. Now, if you were doing this in a microkernel world, okay, so you have the file system as a separate user mode process, and the hard disk driver is also a separate user mode process. So how do these things communicate with each other? Well, now you start having interactions between these various processes, typically through message passing. Okay? So IPC, inter-process communication, we send a message from the text editor to the file system saying, hey, I'd like to do something with this file. And the file system says, sure, no problem. And it turns around and it interacts with the hard disk. Okay? So you can see how this is kind of expensive, right? This is not free, and in fact, it's kind of costly. It adds up really fast. And of course, what happens when the file is created and various operations are taken care of is you have messages coming back. Okay? And so you have this constant interaction between user mode and kernel mode. Now, message passing is interesting. Asynchronous. I send somebody a message. Now what? Well, I can go do other things while that message is being handled, or I could call receive and wait for another message to come back. So I have a choice about whether that interaction is synchronous or asynchronous. Okay? But basically, process B queries the kernel to receive the message. So you might have a send call and a receive call. I call receive, and maybe the kernel will block the process until the message shows up for the process. Or I could have that be a non-blocking call and say receive, and then it just returns and says there's no message at this point. Okay? You can do this in a lot of different ways. Historically, there would be kernel-level queues. That turns out to be kind of the most expensive way, but you imagine the text editor sends a message to the microkernel. Well, until the file system process actually asks for that message, where's it supposed to be? Where's it supposed to go? Well, the kernel kind of has to hang on to it. So the kernel can have a queue and queue up these various messages. And then when a process asks for, what messages do I have, the kernel can hand them back. Okay? So a very simple abstraction. But you can imagine that the implementation details can get pretty costly. Okay? Like here, we'll talk a little bit more about this in the future, but you can have even things like, is so-and-so allowed to send me a message? Okay? So you can actually control one process is not allowed to interact with another process unless the process agrees to it and so forth. So we'll talk about CMU Mach. That's a great example. It's kind of the classic microkernel operating system, and it has a very sophisticated mechanism for permissions and so forth. Okay? Any questions about this abstraction right now? Pretty straightforward, right? Okay, benefits. Pretty obvious, very reliable. So basically, the stuff that lives in kernel mode, that's the code that can bring down your entire OS. So the less of it there is, the happier you are, because it's easy to get all those bugs out. Okay. If a service crashes, okay, no biggie. It's a user mode process. I'll just restart it. So these OSs tend to be extremely reliable because if some important part of the OS dies, you just restart it. It's no biggie. Now, there is a caveat here, which is that just because you can restart a process doesn't mean that you don't lose state or you don't corrupt state. So that's what I'm saying here. And the solutions are always the same. Basically, you just figure out how to build things in a transacted way. Okay? So there's a lot of different techniques you can use to build reliability into these situations where software systems fail. And sadly, we don't really talk about that in this class. There's a great book by these two guys, Jim Gray and Andreas Reuter. I don't know if any of you are excited about this kind of thing. I love this kind of thing. Because figuring out how to make unreliable systems reliable is quite an engineering challenge. But anyway, they have a book called Transaction Processing, and they talk about how to build reliable software systems across a wide range of areas. It's generally applied to database systems primarily, but they actually talk about a transacted file system in their book. It's a great, great book. Okay. This is another really interesting one, and this is one of the appeals of microkernel architectures from the very beginning was, wow, if we build operating systems this way, then it's really easy to split them across cores. It's really easy to split them across processors. It's even easy to split them across computers on the network. Okay? Because this was the thing, they were starting to build computer systems with multiple processors, and they were starting to run into difficulties getting monolithic kernels to run on multi-core systems. But if you have a microkernel architecture, it makes it very easy. Okay. You can also build non-local IPC. If I have an API call where I say, hey, send a message to this other process for me, well, if the OS provides an abstraction where that process can be on the same machine or it can be on a different machine, well, now I have real power. I can actually run an operating system that spans multiple physical computers. Okay? And so, you can build all of this stuff really easily. Okay. Now, I think it's called GNU Herd. I don't know if anybody's familiar with that project, but that's actually an example of a system that supports non-local IPC and can actually run on clusters of computers relatively easily. So, pretty neat approach. You can see that it has a lot of really interesting benefits and upsides. Here's the issue. It is dog slow, and I don't know what else to say besides that. Now, part of the problem, I'm going to point this out in a second. But let's talk about this first. Message passing is asynchronous, but you'll notice that a lot of these interactions, especially the one that I used to illustrate, I'm a text editor. I need to create and save a file. Well, that's a synchronous interaction. I want to call, and I don't want to come back until the operation's completed. But we're modeling that on an asynchronous set of abstractions here. So it gets a little bit expensive here because of that mismatch in your abstractions. Okay, so the microkernel is involved a lot. We have a lot of trapping back and forth. You can imagine I'm switching between processes. Well, that means I have to change the virtual memory configuration. That means that I'm flushing caches, or I'm not able to use caches in as I do my context switches. So it incurs a lot of cost, and that's just really lame. So since we do have these synchronous interactions, it'd be nice if we had a synchronous abstraction that we were using here. Okay. So you can see that this IPC mechanism, at least as it's described, is not great. Okay. Now, part of the thing here, and I hope you'll all notice this, is I described it in a certain way. This is how initial systems try to approach the problem. But you don't have to provide a microkernel architecture with this specific abstraction. And that's something that Liebke noted when he started exploring this area. Okay? So this is a way of solving this problem, but it's not the only way. Okay? So CMU Mach, I mentioned, this is probably the most widely known microkernel OS. So project at Carnegie Mellon. And so what they did is they started with BSD Unix. This is a very smart approach. And again, if any of you, and by the way, if any of you do want to do a CS81 project in operating systems or anything like that, I'm perfectly happy for you to do that. We even have a Rust OS that is currently coming along that we would like to use to replace Pintos, because Pintos has been around since 2005. We'd love to have something that's 64-bit, multi-processor, and so forth. So if that's interesting to you, let me know. But anyway, they did this in a really clever way. They started with BSD Unix, and they basically started adding facilities to BSD. Okay? So that they could continue running this OS. They completed the IPC mechanism, and then they started migrating chunks of the BSD kernel out of kernel space and into user space. Okay? So finally, with Mach 3, they got to real microkernel OS. Okay? And so people got really excited about it. For all the reasons that I just told you, I can run this on a multi-core system easily. I can run it on a multi-computer system if I want to actually run it on a cluster of computers. But it was slow. It was terrible. Okay? And this was the sad thing about CMU Mach. So here's a little bit about the abstraction. You'll notice it's very similar to what I just described about how people tend to approach this. So you had ports. Ports were basically endpoints that processes could listen on for messages. So you could create a port. You could say who's allowed to send me messages on this port. So you could have two processes that only communicate with each other over a particular set of ports. Or you could have a process say, I want to listen to anybody on this port. If you're the file system, you would want to have a port that anybody could send to, and so forth. Okay? So you had things like that. Messages were structured data. Now, part of this that I want you to notice is when I say structured data, definitely requires some memory storage to hold all that information. So maybe you have a struct, and the struct says I've got a field saying who am I and where am I sending this message to. Here's payload data. Here's the body of the message that I want to send. And that would be a thing. Except it was slightly worse than that, because you'll notice you could have additional data containing arrays of values or pointers to more data. So it's not just sending one thing. It's sending maybe, a small graph or tree of data to another process. So all of that stuff has to be collected together and then sent through the microkernel to another process. Okay? So that starts to get expensive. Okay? That was an API call, Mach message, and that was a thing that was used for exchanging these messages. Okay? Notice it could be a blocking call, and you could use it for either asynchronous or synchronous style interactions. Now, part of the problem is the fact that we're sending these rather large messages and rather complicated messages that generally require memory management and memory interactions. So if you're going to allow, as an example, the sender to send a message and then write to that memory address. Think about it. The sender is sending the message, and then they may turn around and write to that space because they want to send another message to someone else, or they want to free the memory so they can use it for something else. But the receiver hasn't received the message yet. That's tricky. So we need to make sure that either the kernel gets a copy, or maybe we can use a copy on write technique, or something like that. So basically, this set of constraints, design constraints, made it a little bit challenging to support easily. Okay, so Mach 2.5, let's see, yeah, so kernel would map the messages virtual pages into kernel space, copy on write. So now, if the process wants to write to them, no biggie, the kernel can go ahead and make a copy, and it'll have a copy, and the user process can go on doing its thing. The sender writes, yeah, so that's obvious. Okay, when the message is received, the kernel maps the message's virtual pages into the receiver's address space. Nice thing about this, does not require copying data. It's funny because when we're talking about IPC mechanisms, what your limit is really what's your bandwidth on your memory bus? What's your bandwidth on your data bus? You'd like to move data as quickly as possible, but what's even faster than copying data on the data bus is not moving it at all. So if I can do things like mapping pages into a process's address space, that's eliminating a copy. Ideally, I copy things at most once. Okay? So that's the ideal. Now, Mach 3 basically said, well, this is too complicated. Yeah, we're trying to make this faster, but it's too complicated to get correct. So basically, it always would copy into the kernel and then just map the page from the kernel into the user space of the receiver. So this is still just one copy. Not horrible. It's just always increased. So now it's consistently one copy. All right? So that's the design. Now there was another thing that they ran into with Mach 3 that made them really sad, which is that they found that, remember we talked about separation of policy and mechanism? So we're going to factor the pager, the virtual memory pager, out into a user process. We're going to factor out the file system cache into a user process. We're going to, ideally we would even factor out the thread scheduler. They started noticing that when these things were living off by themselves in a user process, they no longer had access to all the information they needed to make good decisions. That was a major issue with Mach. So user mode memory pager, kernel needs a page. It needs to figure out what page it can evict, so it asks the pager. So maybe I can change out pagers depending on the way I'm using the OS. Databases actually complicate this significantly because they do a lot of sequential scans. And sequential scans, if you have a sort of an unintelligent pager, then they can make really bad decisions in the context of scans. And so maybe you have a more clever pager if you happen to be running a database server or something like that. So the issue was that they ran into was that the pager didn't know what the rest of the OS was doing or what even was part of the OS to be able to make good paging decisions. And they found that the pager made awful decisions in sort of the most crucial times when you don't have very much memory available. So that was a really sad situation for them. Okay. Conversely, when you have a monolithic architecture and everything is in the same giant box, well, it's pretty easy to make those subsystems make better decisions. So that was one of the really interesting findings that they ran into with CMU Mach. Okay, any questions? Now, I guess a question that I have when I look at this is this inherent in the system design, or is this just poor implementation choices? You know, and that's one of the things I want you to think about, because this whole question of microkernel architectures being useful or not being useful, to me, is still open. You know, even though people have been banging on it for decades now, to me, I'm not convinced that this is a dead problem yet. So I think it's definitely worth thinking about more. So Mach 4, you know, I think Mach 4 was the fastest they went. This was sort of the last one that they tried to improve on Mach's performance issues. And you'll notice, what did they do to try to solve the problem? Well, microkernel is great in abstract, but it's got all these practical limitations. Let's move away from microkernel and move back toward monolithic. So that's what they started doing. Okay. Now I mentioned Jochen Liedtke, and he started looking at this stuff. And again, like I said, part of these problems are inherent, and part of these problems were just design issues. I don't know if I would go so far as to say poor design, but certainly the abstractions that were chosen were too complicated for the actual needs. Okay. And I think that's one of those fundamental things you have to think about when you're designing a solution for a problem. Am I making the solution way too complicated, and is that actually causing me problems? So he started designing a family of microkernel operating systems. So L3 and L4 were the two that he was able to come up with before he unfortunately died. And he was really studying this IPC mechanism, and he said, you know what? You're doing so much extra work that you could eliminate by having a better design. And so that's what he really focused on. And notice here, order of magnitude performance improvement. That's what he was able to achieve just by redesigning things to be a little bit more clever. First of all, he said, basically all of these interactions are send and receive. So why don't we just make everybody use that kind of a system call interaction? Okay? So I trap into the kernel, I say, hey, I'm sending a message and I'm expecting one back. And so now you have one trap into the kernel instead of two, to send and then receive. Same thing on the other end. Well, I'm going to receive and then I'm going to send something back. So why don't I go ahead and do that in a single system call instead of two system calls. So that was an obvious one. So Mach also had this capability. L4 basically always did copy. This is really crazy to me. So previously, if we were trying to send a message, well, I'll go ahead and copy that into the kernel, and then I'll map that kernel page into the receiver's address space. Why don't I just map the receiver address space into the sender and copy straight into the receiver? So now the kernel's not even involved, really. Okay? I mean, it's involved, it's orchestrating the interaction, but it doesn't need to manage the buffer pages at all. Okay? So it just copies direct from process A to process B. That's pretty clever. Also, many of these IPC messages were short. Remember I talked about the Mach message thing, and it would have details about who's the sender and the recipient, and here's a payload, and here's extra pointers to extra data. It's like, why do I need to do all that if I can send a very small, short message packed into registers? I mean, to me, this is like blindingly obvious. I don't know why they didn't do it this way at the start. And maybe, if they had, it would have been wow, microkernels are actually much cooler than we thought, that kind of thing. So basically, this produced a huge performance improvement. If you still need to pass a buffer, that's totally cool. But since most of the time, like if you think about it, you're all seeing this with these system calls that you're implementing for your command shell. I need to do this. Here's an int saying whether it succeeded or not. Okay? There's no reason to pass that back in a giant message. Shove it in a register and be done with it. Okay? So that's the way that L4 would handle these kinds of things. Okay? Here's another one. This is one that I think is really innovative and cool. So I'm doing send and receive. I send a message to somebody. Maybe I'm asking them to do something on my behalf. What am I now able to do? Nothing really, right? I'm waiting for a message to come back. The receiver, they just got a message. What are they now able to do? Well, they're able to receive the message and then do things, right? Well, if I know that I am now becoming blocked, I had the CPU, and I just became blocked because now I'm waiting for a message to show up, and the receiver that I'm sending to just became unblocked, well, why don't I just switch to the receiver and let them start running on the CPU? I haven't had to call the scheduler. I haven't had to ask it, hey, what process should run? I haven't had to do any of that. Okay, so that's a direct process switch. Okay, so process A performs send and receive to process B, and it's blocked. Process A is now waiting for B to reply, so A is now blocked, but B is no longer blocked. So no reason to invoke the scheduler. And this was really nice. Now, what's an obvious issue with this? Yeah?
If B is in the middle of processing another signal?
B could be in the middle of doing something else, but let's stick to single core just to make our life simple and say B is, we know it's blocked on a receive, and so like this is like a lot of simplifying assumptions. And we also know that, we can give it the CPU because it's not on some other CPU in a multi-core system.
And it's also not preemption.
Yeah, preemption is the big question here. We're kind of making a giant assumption that process B is the best process to get the processor next. We see that. So by not invoking the scheduler, we don't know whether that's the case. That's kind of an issue here. So that was the one sort of drawback of this approach, which is that if we have a real-time or a soft real-time system, or we have a priority-based scheduling system or something like that, well, we can't necessarily make the same guarantees that we could before, because not invoking the scheduler means somebody may not get the CPU that actually should get it, okay? Or at least not right away. Let's put it that way. There's plenty of ways you can mitigate this. Like you can say process B is constrained to process A's time slice. Like it'll just get the remainder of process A's time slice. So in effect, process B is running on behalf of process A at that point. Something like you can make choices like that. But then, of course, if you have some kind of scheduler that classifies processes based on their behavior, that makes things complicated as well. So you just have to be careful about how not invoking the scheduler affects the guarantees you can make regarding scheduling. Okay, any questions? Yes?
If you're not entering the scheduler and you start other processes, for example, A calls B and then B sends something to C,
sure.
How does the scheduler keep track of all these processes that used to be blocked according to the scheduling queue?
Yeah, so here's the thing. That's a good question. The thing is that process A is still going through the kernel to get to process B, and process B is still going through the kernel to get to process C. So you'll learn this really soon. The kernel knows everything. Like it has access to the hardware. It knows everything. It knows every process that gets the CPU. Most processors provide mechanisms to say how many instruction cycles have I held the processor for. So you can actually get very detailed information about who's gotten the CPU. And so the kernel can record that stuff so the scheduler can make good decisions. And so that tends to be the way that these things work. Obviously, at some point, the kernel can still intervene and say, okay, enough direct process switches. It can say, for example, we've gone so long without having a scheduled process switch, so we'll invoke the scheduler now. So yeah, it's amazing. The OS knows everything. Like it's the smartest piece of software in your computer. All right, any other questions? Alrighty. see. Sure, I don't lose track of the time. Okay, so obviously, leaky sort of reinvigorated microkernel implementation. And it was interesting because they noticed that with these approaches that it started to break down some of the isolation between processes and obviously with the kernel as well. And so they started noticing that, well, this is reducing reliability, but if it's still better than a monolithic approach, then hey, that's not bad. Okay. And it turns out that L4 variants are used in a lot of different places. I can't tell you an exact list of mobile phone companies that use, I think Ericsson might be using L4 microkernels on certain things. But you should look it up. If you're curious about this, you should totally look it up because it's pretty interesting. But they're definitely getting some utilization in various places. If you want to find a company that's using L4, sort of continuing to extend this software approach, then there's an example. And also, the L4 microkernel is available itself if you're interested in poking around in it and seeing how it does things. Pretty neat. Okay, so we said microkernels are awesome and reliable, except they're really slow. Monolithic kernels are fast and giant balls of mud and fragile. Okay. So given that we have these two extremes, you can imagine that there's some blending of these that one could achieve. So like I say, important OS services live in user space. So if I'm having to interact between these services, then that's going to require IPC and context switches. So hybrid kernels have the same idea, except they allow some of these services to be moved back into the kernel. And so this is a really interesting thing. You move these services, well, now you're sort of reducing the reliability of your kernel, but you're also improving the performance. So you'll notice that hybrid kernels and modular kernels seem really similar, except that the difference is that modular kernels require that kernel module to be in kernel mode, and hybrid kernels allow that module to be in user mode instead. So that's the distinction between the two. Okay? We got that? So that's OS X has a hybrid kernel. NT is an example of a hybrid kernel. So you'll notice, Mach was a great idea. Everybody got so excited about Mach, and then they all sort of jumped in, and then they started tiptoeing back because they realized that this is not fast. So basically, we'd love to have these facilities outside, but we have to migrate them in to the kernel to make things fast enough. Same thing with NT. So when NT was being designed, CMU Mach was well underway, and they tried it, and it's like, oh, this just isn't fast enough. So they started migrating things back into the kernel. Okay, the one that's I think most interesting is Chorus. There's a few microkernel OSs who have this notion of colocation. The idea is that you can have a part of the OS running as a user mode process. And you want it outside of the kernel because it's not done yet. It's not fully baked. And so you work on it, and you work on it, and you work on it, and once you feel like it's reliable enough, then the OS itself has a facility for bringing that into the kernel so that it is now tightly coupled, and now you have fast interactions with the rest of the kernel, very modular design, and you don't have trapping, you don't have context switching, so it'll be very fast. Okay. Like I say here, most of the microkernels that do this only support colocation at compile time, so you get back into that whole, I've got to rebuild my kernel to colocate something. But Chorus is fun because it can do it at runtime as well. So there's another OS if you want to look at an example of a hybrid OS. Okay, questions? So there's that. You can see how these things would all fit together. I think this is the last one to talk about, the last abstraction. This is where it starts to get wild. You'll notice that all of these OS kernels impose a specific set of abstractions on your computer hardware. They take away responsibility of managing the hardware so that, you'll see this in Project 2. I want to get into this weird graphical mode. Well, all you have to do is make a call and say, hey, I'd like to get into this graphical mode. You don't have to send all the little values to the little ports on the VGA controller or on whatever graphics controller to switch the computer over into that graphical mode. It takes care of it for you. So yeah, file system is a great example of that. So there's another design approach called an exokernel. Exokernels allow applications to decide how they want to interact with the hardware. So it answers the question, what if the OS didn't force us into a specific abstraction for interacting with hardware? Okay? So this idea came out of MIT, 1994. That's back when a young Donnie was getting ready to go to college. And the idea was that the application could make choices about how to manage hardware that might be better than the OS's choices. That was the whole idea. So let's just give applications total control over the hardware. So the OS basically has one job. You know, it does the whole like process abstraction, process isolation, blah, blah, blah. It does all those things, of course. But then it also has some capability to multiplex the computer hardware across multiple applications. But that's it. No abstractions. Just you get this part of the disk, you get this part of the disk. Don't stamp on each other. Things like that, but really it was up to applications to use the hardware however they decided. Okay? So that's the idea behind an exokernel. Yeah, and this is kind of the important detail here. Exokernels, like whether something is an exokernel or not, is kind of orthogonal to whether it's a monolithic kernel or a microkernel. Although almost always these were microkernels. Okay. So, interesting approaches. These exokernels tend to provide common facilities using library OSs. Library OSs were basically ways of interacting with computer hardware that most people like. So you could use the library OS, but you didn't have to. And so applications could either run on top of library OSs or they could provide their own. Okay. So there was the experiment that was done at MIT was creating this OS called XOS. So that's an exokernel operating system. It had a libOS, or a library operating system, called XOS. So the spelling is slightly different, so we have EXOS on top of XOS. And basically, XOS would implement, XOS, the library OS, would implement your system calls like open, read, write, close, sync, all of those kinds of operations that you are all learning to love. And so once you have that, then you can run basically most open source software or anything that uses the Unix standard, you can run easily on that OS. Okay? So that's pretty cool. Now I can compile, now I can run things using this library OS. At the same time, I can create applications that don't need to use those abstractions. So they created this web server called Cheetah, and you'll notice file system management. It did its own file system management. It would make sure that parts of a web page that needed to be served at the same time were co-located on the disk. So that I don't have large seeks when I'm pulling data off to send to the client. They had their own TCP implementation, so they built their own networking stack. And the networking stack was aware of HTTP, so it was able to take advantage of what state it was in on the HTTP request response and so forth to make sure that I can minimize the number of packets I have to send. And when I do need to resend stuff, I can do it straight out of the file system cache because I have access to all of it because it's all mine. Okay, so this was the idea behind Cheetah. And they found that, again, they got up to an order of magnitude performance improvement compared to equivalent hardware at the time. Now, I want to ask you a question. Does it seem like a great, because you can see from these various experiments and these various approaches, it kind of seems like what I'm saying is it's really bad to provide structured or modular software systems that separate concerns. The more we blend things, the faster it goes. Well, you probably all have thoughts about that spectrum, right? And hopefully you can see that on one end of that spectrum is a highly modular, highly structured design that separates concerns very cleanly and forces everybody to interact through very clean, well-defined interfaces. On the other hand, at the other end of the spectrum, you have everything special coded, purpose coded, and it's like blazingly fast. That's kind of always the spectrum that you have in these software systems, and you always have this tug between the two. I want it to be really performant, purpose-built, but I want it to be modular and reliable and safe and all of those kinds of things. So these are various experiments that have been done exploring different approaches to operating system architecture. Like for me, I tend to really subscribe to the whole notion that you optimize things when you have to. You've probably heard the saying, premature optimization is the root of all evil. It's a good thing to live by. I see a lot of new software developers who optimize things before they know they need to be optimized. I mean, if you're optimizing a code path that your program isn't even spending a lot of time in, you're wasting time, and you're making your system less reliable. So those, that's an important thing to take. But you can see how people have been exploring these various options over time. All right, let's see. Yeah, so it's pretty interesting. If you want to see more about this, here's a link to MIT's Operating System Research Group. I don't know how much current research. What you'll sometimes notice is that when graduate students move on, the research kind of ends. They complete what they wanted to do, and then they sort of stop exploring that particular topic. But there's a few other exokernels that have been attempted. You have Nemesis. So Nemesis started out as a software project to do multimedia processing, and they just found over time that, like, wow, this is a slow operation, this is a slow operation. Let's start moving stuff into the kernel to, did I get that right? Yeah, I'm sorry. Let's move stuff out. Let's give the application more and more direct control over the hardware. That was the direction that they went. And so it kind of ended up being an exokernel just by virtue of the direction that they moved. They kind of didn't intend that at the start, but that's where they ended up. And then there's also XOMB, which is, I think, much more well-known as an exokernel project. Like that one, I believe, is actually active, and you can download it. You can go look at it and tinker with it. Okay? So let's see. Summary. So these are the ones that generally capture this. Now, you'll notice if you look online, you read Reddit or stuff like that, you'll see other kinds of kernels mentioned. Like, I don't know, nanokernels or other weird, I can't even think of the terms that people use right now. I don't think they're worth knowing because they all tend to be a linear combination of this set of ideas. Okay? This pretty well captures all of the abstractions that people have explored in operating system structure and design. So that's why I think that this is pretty much sufficient for what you need to know. Okay, there is one notable missing example, which is hypervisors. Okay? They're kind of an entirely different beast, and that's why I really feel like they deserve their own lecture too, because they have an entirely different set of problems to solve. Can be quite challenging, in fact. So anyway, are there any questions about any of these?